Now for number 2, in fact this is not a real recurrence relation for an algorithm. There is no algorithm that divides the problem into this size of subproblems, but this is for showing you how we can use methods for solving recurrence relations on this example. This one is a little bit tricky because we need to know what are the values of n so that we can transform it into another form. By looking at some examples of n, so the first value of n is 2. But you know that in recurrence relations, every value is found from previous values. So if I want to find 2, then the next value supposed to be is 4. Why 4? Because under the square root of 4 will be 2, which is the previous value. Now for 4, the next value must be 16. Why? Because the square root of 16 is 4. Now for the next value, it should be 256. Why 256? Because if you take the square root of 256, it will be 16. So it looks like you are raising to power 2 for each subsequent number, because the square root of n should be a perfect square. And this will continue. By rewriting these numbers, we can write it as a power of 2. So this is 2 raised to power 1. This is 2 raised to power 2. This is 2 raised to power 4. This is 2 raised to power 8. And you can expect that the next one will be 2 to the power 16, 2 to the power 32, which is also a power of 2. Again, we can write this one in terms of a variable of the power, since the power are already power of 2. See, 1, 2, 4, 8, 16, 32, they are already power of 2. So we can say that 2 is a power of 2 raised to power k. And the first value of k, I need to get those numbers. So the first value is 2. So how to get 2 from this equation? When k is equal to 0. So when k is equal to 0, we will have 2 raised to power 0, which is 1, and 2 to the power 1 is 2. So the initial value for k is 0. So k will be 0, 1, 2, and etc. So this is what we will start first by assuming let n is equal 2 to the power 2 to the power k. And the first value of k is 0, 1, and 2, and etc. Substitute into the recurrence relation. But before that, we need to know what will be the square root of n will be if n is equal to this value. So maybe we need one more step here. Then the square root of n, maybe I need a space because we will have big power, is equal to 2 to the power 2 to the power k to the power 1 over 2. Now multiply 1 over 2 by 2 to the power k. This will be equal to 2 to the power 2k multiplied by half. And you know that half is in fact 2 to the power minus 1. So this we will have 2 raised to power 2 raised to power k minus 1. We will add the powers. Now when we substitute into the equation, into the recurrence relation, then we will say that Tn equal to the t of square root of n plus 1 will be transformed into t 2 to the power 2 to the power k equal t 2 to the power 2 k minus 1 plus 1. By rewriting the recurrence relation, we will have t 2 to the power k minus 2 to the power 2 k minus 1 is equal to 1. So by looking at k, on the left hand side we have k, beside it we have k minus 1. So this looks like the homogeneous part, and 1 will be the non-homogeneous part. So this is the homogeneous, part of the solution, and this is f of n. Now, if we find the characteristic polynomial, so the characteristic polynomial, first for the homogeneous, it will be x minus 1 because there is no number in here. So if this is like, if you can imagine an, because we have k or ak, and here we have ak minus 1. So the root will be x minus 1, and the root for f of n will be equal to x minus 1. So we have repeated roots. R1 is 1 and R2 is also 1. So the general solution for t 2 to the power 2 to the power k will be equal to c1 plus ak. Now we are finding the general solution for this recurrence relation. And this recurrence relation is written in terms of k because it was transformed. So this is our equation. Now first we need to find the constant k from the particular solution. So finding a from the particular solution. Which is ak. Now ak is the particular solution. We substitute to this recurrence relation in here for t 2 to the power 2k will be replaced by ak, and for this term will be replaced by ak minus 1. So substitute, we will get ak minus a k minus 1, which is equal to 1. From here we will have ak minus ak plus a is equal to 1. So we have a is equal to 1 because ak minus ak is 0. Now we substitute into the recurrence relation. So we will have t 2 to the power k is in fact equal to c1 plus k. Now finding c1 from the homogeneous part, which is from t2 is equal to 1. But we need to know, remember that since n was equal to the power 2 to the power k, now we need to know what is the value of k when this is equal to 2. Notice that 2 to the power 2 to the power 0 is equal to 2. So therefore, k is equal to 0. So if k is equal to 0, then n will be equal to 2. Now substitute for this and to this equation, the one that we have found here. So for k equal to 0, we will have c1 plus 0 is equal to 1 because t2 is 1. So from here c1 is equal to 1, and the recurrence relation that we will have 2 to the power 2k will be equal to 1 plus k. But this answer is given in terms of k. Since in the beginning we assumed that n was 2 to the power 2 to the power k, then we need to find k in terms of n. We will do this in 2 steps. Maybe I should make a space on the left-hand side, make abbreviations by using since, using dots. Then take log of 2 both sides. If you take log 2 both sides, then on the right hand side will be 2 to the power k. And I will write here, take log 2 both sides. Now again take log 2 both sides on this equation. So you will have log 2 n is equal to k, And I will write here also take log 2n again. So we have found k in terms of n. Substitute here, since n is already equal to this, so this value will be tn. This will be tn. And for the one on the right hand side, it will be 1 plus log 2 of n inside log. And this is the solution of the recurrence relation. So we have 2 here.